Hello and welcome to a drive-by code session. This is another one in the series on how to make a programming language. And currently, where we are is we have written a parser described by this grammar, which we've been working on throughout the series, which at this point, it is able to build an AST. And what is an AST? Well, an AST looks like this. An AST is a description of a piece of code. And in this case, we have a parse script, which has been written to parse this expression. That's the code that went in as the input. So looks kind of like this. So the code in this case is 1 plus 1. This is a string as evidenced by the double quotes. We're going to feed that through our parser, which our parser again is sort of specified or written in the form of this nearly.js grammar. And if you need to get caught up on all of this, by all means, please watch the previous videos in this series. But after this string is fed through our parser, then what we get is an AST, also known as abstract syntax tree. And what does an abstract syntax tree look like? Well, it looks like this guy here. We have represented this abstract syntax tree as a JavaScript object in something that's serializable in JSON format, in fact. And we're basically saying the representation of this piece of code here, 1 plus 1, it is a operation. In particular, it's a plus operation. So we're saying this whole thing here, it's a plus operation, and which has a left-hand side and a right-hand side. I'm basically writing out the visual representation of this, where the left-hand side is a number, which happens to be a 1, and the right-hand side is another number, which also happens to be 1. So this sort of graphical representation of this tree, abstract syntax tree, is represented in this way in JSON format. And that's what we have so far. If you want to know how we got here, watch the previous videos. In this video, I'm going to take this AST that comes in this JavaScript format, and we're going to evaluate the answer. So this is, and like I mentioned in the previous video, there are multiple purposes an AST can serve, including you can use it to evaluate the answer, but you could use it to check for maybe errors in the code, in a linter, using a linter or something like that. But you can also use it to generate the equivalent code in another language. In this episode, though, we're just gonna write a function that takes this AST structure as the input, and it should return a numerical result back. So the correct answer for this AST, for example, should be the number 2. So let's see how we do that. Again, Waikit wrote this code. I'm just going to replay what he wrote and explain what he did. So let's get started. Okay, so the first thing he does is he's going to write an evaluate script, which is going to read in this ast.json file, and then it's going to try to evaluate it, I presume. Again, he uses the mz library to read in the file, and I've made a video on using Node with async await to read files using the mz library. So if you want to learn more about that, you can check that out. Okay, so first we're gonna read the file, read this ast.json file. We're gonna use async await to await for the contents of the file, and then we'll turn the string buffer to a string, which we can then, since the content is actually in JSON format, we're gonna use JSON.parse. The native JSON.parse, not the JSON parser that we wrote in the previous episodes, and that's fine. Maybe in some other scenario we'll use our own JSON parser, but that's not the point here. The point here is we already have a AST sort of structure, and we're gonna try to evaluate the answer based on that structure. So if we evaluated this guy, for example, we should expect the result to come out with 2. And then we'll print the answer. Now we need this evaluate function. So let's write this evaluate function. He's gonna just, as a sort of dummy placeholder, return 0 for now, to be able to debug the rest of this script, see if everything's working right. So run this evaluate script, and the answer is 0. Okay, now let's do something closer to what we're trying to achieve here. So nodes, so far in our grammar we have sort of we've created the grammar. The AST grammar contains 3 types of nodes: an operation node, number nodes, and function call nodes, because that's what the grammar supports at present. There are all the places where it has like a type discriminator like this. Okay, so if we want to be able to evaluate a node, then we need to set up handling code for each of these types. However, if it's not a type that we know about, we're just gonna throw an error here. Okay, and we're actually gonna start with the simplest possible case, which is just a plain number. So if you get a plain number in the code, and we'll parse it. So we reparse it, and the AST should look just like that. The code simply represents a number, which is 1. And if we evaluated that, or how do we evaluate a plain number? Well, if we call evaluate function on this number, let me split this up actually. So we're gonna have 3 panel situation going on here. Okay, so we feed this object, feed this guy in here as node. It's gonna fall into this case here because the type would be number here. That matches this. And if we want the answer to be the value of the number, well, easy, just return the value of the number. So let's go ahead and do that. There. And we rerun the script, and it evaluates to 1. So the answer of evaluating the code 1 is 1. That seems logical. Let's do something a little harder. If it's 5, we change the number to 5, then it's 5. That's fine. Let's go back to 1 plus 1 now. So now, if we change the code to 1 plus 1, and we parse it again, then we actually have this AST. So given this AST, we're gonna need to change the evaluate function to be able to handle this. And this time, since the node we're feeding into the function is actually a type of operation, is gonna land in this if statement clause in here. So what are we gonna do? We have to write some code here to make things happen. I'm actually gonna recursively call the evaluate function on both the left hand side and the right hand side of the operation. And what that's gonna do is basically, so this call of evaluate is gonna take node.left, which is this guy, and sort of feed it back into here, in which case it'll return the number 1 here. And same thing happens for the right hand side. So we did the same thing, feed the right hand side over here, and it's gonna return the 1 here. So that actually yields, whoops, 1 in the left variable and 1 in the right variable as well. And then we just have to put left and right together based on what the operator is here. Okay. And we do that with a switch statement. So case plus, we're gonna add left and right together. If it's minus, we're gonna minus. If it's the multiplication symbol, we're gonna use the star symbol in JavaScript to multiply them together, and we also want to support division. So, but if the operator is not something we support, then we're gonna throw an error. By the way, sort of preemptively throwing errors like this is, in general, I consider it to be a good practice because it aids debugging. In case the logic of your code is wrong, it would hit sort of an error if you're, and it will sort of like prompt you to fix something about it before the error sort of goes into a more complex route. Okay, so we get 1 plus 1, the answer of 1 plus 1 is equal to 2 now, and that's great. And what is also great is now this is actually already able to support more complex statements, because if in the event the left hand side happen to be another operation, this evaluate will also be able to handle it as well, because we already have the case to handle operations. And that really is the beauty of recursion here. Okay, let's keep going. So does it handle 2 plus 1? So this is the AST now, the updated, or did we call it 2 plus 3? Oh yeah, we changed it to 2 plus 3, and that's the new version of the AST. And if we evaluate that, answer is 5. So it seems to handle that just fine. All right, let's go back to a 2-pane situation. Okay, so now we want to handle function calls. We want to handle the power function, take 2 to the 3rd power, for example. And that is the AST associated with that power function call. But our evaluate function obviously needs to be modified to handle that case. So we'll say, okay, what is the function name? Now the function name comes from it's called fun name. It comes from this AST note. So if we're gonna assume that if the type of the AST note is a function call, then it will have a fun name, which this example does have. And so if it's POW, we're gonna take the arguments and sort of spread them onto the math.pow function. So we know there's 2 arguments. This map evaluate, by the way, is we know there's 2 numbers here. We want to send these numbers also into our evaluate function so that we can convert this AST node into a raw number. And that's what this clause of the if statement would have done for us. At this point in time, we would have had args be 2 and 3 at here, because the arguments are this array, and for each of the things in the array, we're sending it over to evaluate. So going in here and it would have hit this type checking clause, and it would have returned just the value inside that number node. So that's how we're getting this being 2 and 3 here, and then we just this is equivalent to saying math.pow2, 3 here, given an array, and you spread it over the argument list like this. And while we're at it, we might as well support the other functions as well. And these are all the built-in functions that this grammar supports currently. We have power, square, square root, sine, cosine, and absolute value. So at this point, we can support function calls now. 2 to the power of 3 is 8, and that seems correct. Let's do something else. Sine of 2, and to reparse it to get this new version of the AST, which represents sine of 2, and evaluate it, and that's the answer. I don't know whether that's correct off the top of my head, unfortunately. Oh, maybe I can use my computer's calculator to do it. 0.909. Yeah, so that is correct. It did the right thing. Okay, and we'll do square of 4 minus 3. Okay, he's just testing out some different cases, and now he's actually compounding some function calls with an addition operation, and the AST for that operation is this big old mess. So if you drill into it, it actually should make sense, the way that these operations and function calls are combined. Evaluate it, and it gets us an answer. So all of this seems to be working, and yeah, and that's how you take an AST, which is recursive in nature, and use a recursive function to handle the AST traversal. One thing I want to illustrate a little better is how recursion works. So let me give another example. So let's use like a semi-complex expression, such as 2 times 5 minus 2. Let's say first of all, let's parse it. And okay, so we parsed it, and this is the resulting AST, which yeah, and I mean I can depict it visually as something like this. So at the top level, there's a multiply operation, and then on the left hand side is a number 2. On the right hand side is yet another operation, though. It's a minus. The left hand side of the minus is a 5, and the right hand side of the minus is a 2. So this is 2 times the result of 5 minus 2 is our operation. And just so you can see it, the original code was that. Okay, I'm gonna draw the stack frame representation, which is how your program keeps track of its state while it's executing. And every single time you call a function, it actually creates a new frame in something called the stack. So initially, you're actually running in main stack frame. I'll call this the stack frame. The stack frame is where the function stores all of your variables that are present in your function. So in the main function, we actually have a few variables. We have content, result, and AST. So it will actually look like this. Content, make a little table here. Content actually is gonna look like exactly this in the form of a string. The AST is gonna look like this guy here. That is the AST, or at least the visual depiction of it, but the more literal version is this. It's this complex JavaScript object is what AST is. The result is still waiting for an answer, or waiting for a value, I should say. So we created the result on this line, but not before the evaluate function call finishes. Okay, so now on this line here, evaluate gets called, and when that happens, JavaScript is gonna create another stack frame, which is something that happens whenever a function is called. And evaluate is called with AST as the parameter. So the parameter that goes in is actually this same structure, the same AST structure goes in to evaluate, and we're gonna have to sort of create another table for evaluate to use. And so far we don't have any variables defined, but the first thing we're going to do is do this if statement, right? So if statement, is this guy a number, the entire AST, and by entire AST we starting from the root node here, right? So the root node is actually a multiplication operation, so it's not a number, it's not going to go in here. It is an operation, so this is where it will go. And so then it's gonna evaluate this line, which creates another evaluate function call, but passing node that left into it. So JavaScript will actually have to make yet another stack frame and yet another table just to evaluate the left value of this multiply operation. And what goes into here? Well, that's the left of the multiply node, which actually is just this guy that goes into here. So now we're in the same evaluate code again, but only this time is not with the entire AST, but with just this 2 node within the AST. So now we're gonna do this test, note that type equals number, and that is gonna be true. So it's gonna land in this conditional here. It's just gonna return note that value, and so I'll say it's gonna end up with the return value of 2 here. Okay, and when that happens, the return value of 2 comes back. This guy can get erased because the job of this previous evaluate left call is done, and the return value 2, it gets assigned to left. Okay, so we're done with this line to evaluate left, and we got the value of 2, the number 2 for the evaluate call to this sub node 2. But the next line is yet another call to the evaluate function. Now we're trying to get at the value of the right hand side, or the numerical value of the right hand side. But in order to arrive at that, we need evaluate to do its job yet again. But this time to node that right. What is node again? Well, the node in this case is actually the entire AST tree again. So the right hand side of this multiplication operation is that guy. So we're feeding that guy into evaluate this time now. And what is that guy? Let me make a table for this guy. This guy is yet another operation. So this time around, it's going into this operation clause of the if statement yet again. And it's gonna need its own left and right. So left, how do we get the answer for left? We need yet another evaluate call. And you can see we have more and more stacks stacked up. And in fact, we'll have as many stacks of evaluate calls for the height of the tree, because this tree is 3 levels deep, 1, 2, and 3. We'll end up having 3 levels worth of evaluate calls deep in the stack to handle all the way down. So this time evaluate for the left hand side of the subtract operation is going to be this 5. So 5 is going in here. We need another table. We're going to have to like move over here to keep going. Okay, but anyway, the 5 though, because that's a number, it'll hit this branch here and just return the value 5. So the return value here would be 5. Actually, we can actually cross this out because we get a return value. Return value is 5. This gets crossed out and we're back here because the previous one was waiting for the left value. So 5 goes into the left value of the parent stack. So 5 goes into here. And let me erase all of this stuff now. Okay, so now we're here and we have completed this line, and the next line is gonna be that. So we're gonna make a right variable here, or slot for the right variable. But in order to get its value, we need yet another evaluate call. And this time, note that right, because note, we're talking about this subnode here, because that's node here. The right of this subnode is this number 2 here. So this time it's the number 2 number node that's going in. We're gonna make a table here. No, because it's a number, it's gonna take this branch and it's just gonna simply return the node's value, which is 2. So the return value is 2, and because the function returns now, or this version of the function call returns, this is gonna go away. This 2 will make its way over to here in the parent version of the evaluate call. That was this line here, and the 2 goes in here. So now at this point we have the numeric value for both the left and right value at this point, and associated with this minus node. And then what this code is going to do is select one of these branches. In this case, it's going to select this one because the operator is minus, and it's going to perform this subtraction with the ready numeric values here. So, and it's going to return that. So I'm going to make a slot for the return value, and the result of 5 minus 2 is 3. So now, because this function is returning now, this stack frame can go away while taking the return value 3 and returning it to the parent. And in this case, this whole operation was done in the parent version of the function call for this line, because it was calculating the right hand side of this multiplication operation here. So the 3 belongs in this right variable here. Okay, let me erase this frame now. And we have the numeric value of both the left and right hand side of this multiplication operation. And we just got done with this line basically. And again, we're gonna select one of these operation paths to go down, and this time it's going to select this one because it will have a multiplication symbol, and it's going to return the result of left times right. So the return value is going to be 2 times 3, which is 6. And again, because we have returned from this function, this guy can go away. Oops, this guy can go away while taking this return value and sticking it back over here over the main function, because the line that actually kicked off this entire series of events was this call to the evaluate function with the entire AST tree. And the final answer is 6, and the 6 is gonna it's the return value of the evaluate function gets assigned back to the result variable over here, and therefore the final result is 6. And so this is the final state of things, and because we console.log the answer, I'm gonna expect this program to produce on the console the answer is 6. So why don't we actually execute the program now and see if we are correct about that. And it is awesome. Okay, so that's how this evaluate recursive function works. I hope you enjoyed it. And the next time, what we'll probably do is, instead of evaluating the answer, we'll make a code generator that will generate the equivalent JavaScript to execute or evaluate this expression. So if you're interested in that, I will see you next time. Thank you.